Nathan. So welcome back everybody, and let's start our next lecture, which is on the conversion of ASTs to the quad IR, which is the first topic we are looking at after the intermediate course understanding, and then we'll try to finish it hopefully today, and then get into the next topic beginning next week, which is how to take this linear IR and then convert it into a form which is amenable for doing some transformations. So remember, so far we have just been translating. First we did all the analysis of syntax, semantics, and lexical specifications and so on. So no translation was involved there. Then we had parse trees, and from there we are now doing this conversion from the ASTs, which is representation of parse trees without the non-terminants, and taking that representation, which is what we call as tree representation, and then converting it into the linear representation. And our target here is standard target, which is the quad representation, operands and then operator and the destination, which is close to the way the instructions will get generated, and that's the idea. And as I mentioned, from there we will convert it into the control flow graph and then do some transformations on those. So last time we started looking at it, and this is a typical repertoire, and you can see it is a machine-independent representation of quad, typical operations, arithmetic logic operations involving two or single operands, and then some indexing operations for data moment, and then conditional transfer of control, such as the first one. If that particular statement is true, then go to a particular label X, otherwise just the unconditional part of it, and so on. And function calls, which in terms of parameter passing, etc. So you can pretty much see that our regular constructs which we have in our programming languages, such as if-then-else statements, assignment statements, all kinds of different loops, etc., could be transformed into this particular representation. And this is the example which we had quickly finished at the end of the last lecture. Which we showed that we have an if statement. Inside that we have a while statement, and then we have an arithmetic operations, of course, which is a part of the assignment statement. We have an else part to it, and so on. And from there we saw that this is the representation which is generated by taking this source code and then converting it into the quad IR, which is shown on the right hand side. And what I did not show here is, of course, AST representation of the source code, but that can be very easily seen knowing our grammars and the parsing and so on, that you will topmost level you will have an if statement sitting there when the parsing starts, and then from there there will be a conditional part of this if statement, there will be else part, and within the bodies of these if and else part, you will have the corresponding things such as the while part, while statement, so that will descend down to another while statement which is in the body of if. And on the else side, we'll have a simple assignment statement, which is consisting of a left-hand side variable and a right-hand side set of is an expression. And each one of them, so going to the while statement, will have a conditional or a predicate there. And then again, in the body of the while, we'll have a statement or statements. In this particular case, a single statement, and that happens to be the assignment statement here again. In general, that could be any other statement. So in general, that could be another if statement, that could be another for loop, while loop, etc., etc. So you can envision this left-hand side source code being converted into a parse tree or an AST representation with the corresponding nodes. The topmost node will be if-else. Inside the if side, these body of ifs will have a loop, which is while. And then on the else body of the else, we'll have an assignment statement. And again, in the body of while, deeper down in the parse tree, we'll see an assignment statement and so on. So this is very interesting because this is pretty much the basis of how the code will get generated on the right-hand side. At a very high level, what will happen is we'll start at the topmost level of AST, and we'll descend down, going deeper and deeper inside in a particular way. So for example, we will take up the body of if statement, and we'll do certain conversion, and we would have generated some code for the while statement. For generating the code for while statement, we would have generated the code for C is equal to C plus 2 statement here, and then we'll wrap up with a code for while. That code for while will be passed on to the top level if statement, and similarly the lowest level on the else side, we would have generated code for C equal to n times n plus 2, which is shown here. That would be passed on to the else side and will get wrapped up by the corresponding else side of the statement. And at the during this particular process, in short, we'll descend down, we'll go to the root levels, we'll generate code there, we'll pass on that code back up to the next higher level, or one level up from root, from the leaf, and that's where this code will get stitched to the next level of statements. And in short, we'll keep going up and up and up in this particular tree, and finally we'll have the whole code going towards the root. Again, we'll start at the leaf, descend down all the way down to the leaf, generate codes for respective statements. That statement will be told to us by the nature of the IST node, whether it is an assignment statement, whether it is a while statement, whether it's an if statement, etc., etc. Using the kind of statement that we are dealing with, we'll have templates for code generation, which will fill up. Once we go up one level, that code will be passed on to the next level, and we'll keep going up in a post-order manner, and we'll generate the code for the whole of the construct. So in short, we'll start at the leaves here, which are C equal to C plus 2, generate code for that, wrap it up by going to while, and then that will be passed on to the body of if. And similarly, on the else side, we will start with C equal to the assignment statement, C is equal to n times n plus 2, generate that code that will get wrapped up at the top level for the if-else side. And these are shown here in terms of the control flow that is getting generated. Of course, we had seen how this particular thing works. So now let's look at how the code generation mechanism that I just mentioned is really implemented by descending down the trees and by using the corresponding templates for each one of these types of statements. So, we have high-level IR, which is basically AST, as in our case, with nested structures. And we are generating here the quad, which is everything is explicit. It is as shown on the right hand side here, as though it is a sequence of machine independent statements which are going to execute in that order from top to bottom, and each one of them will generate partial results which will be passed on to the next statement that is generated will get used there, and together it will generate the code which will execute the statements on the left hand side. So just to give an example, at the assignment statement, consider that here C is equal to C plus 2. Nathan, can you hear me?
Yes, you're back now.
I hate this. I don't know what the network problem is. Anyway, hope we don't get interrupted again. Okay, so in terms of going into this details, we are embedding generated code inside the outer level of the construct, and we keep going up, as I mentioned. So we have this particular problem, and let's see how we can solve it using a systematic algorithm which makes use of these templates for each of the constructs and for each of the kinds of statements that we are dealing with. And we are able to do some bookkeeping in that process of generating intermediate results and labels and so on. So the basic mechanism remains the same at the high level. We are going to define a translation algorithm for each AST node, and different AST nodes being either an assignment statement, an if then else statement, while statement, for statement, etc. And we are going to assume that we have similar code generation mechanisms for each of the children. We'll generate the code for those, and then we'll stitch it up using the translation procedure. And again, we'll go from bottom up in this particular case. So towards that, we are going to define what we call as a generate function for each of the kinds of AST nodes. And we'll generate the calls, or we'll have the calls for the children here from the top level AST node that we are going to deal with. And each one of those calls will descend down as per the order of the calls. We'll keep going down, and we'll generate the code at the lower level and then come back up, and then using the values which are passed from the lower level calls, we will put together the higher level call. So that's the whole idea. And the stitching function will take these generated code and their values which are returned from them, and will put together the higher level function for each one of these nodes. So that's the idea. So when we deal with these things, we'll start with how to generate code for an expression. And that will give us a very good idea, because what we'll be doing is we'll take that expression as organized by the parse tree or the AST, and we will take the components of this expression, which are sub-expressions. We will hold the results for the sub-expressions in a temporary or temporary symbol, and then we'll send that symbol up to be combined with other symbols or temporary results. We'll combine them, and we'll keep going on and on and on, and that's how we will we'll generate code for these expression or an expression tree. So here is the example of, and the things remain the same pretty much for any kind of expression trees. We are illustrating this using arithmetic operations here, but similar things are possible for logical expressions and any other kind of expressions that we deal with, because they have the same grammar, and there, of course, the operator differs there. And based on that, we will, of course, deal with the implementation slightly in different ways. So here is a question of how do we combine two sub-expressions. One is on the left-hand side called sub-expression 1, and the second one is sub-expression 2, as shown by this particular box here, and define the process for taking the code generation and carrying that out. So as you can see here, this is the AST representation for expression 1 and expression 2. And in general, what we will do is when we come to this particular node, we will know that this is an arithmetic expression with a certain operator. We'll know the properties of that operator. We will, using the properties, first evaluate expression 1 in some cases, generate its generated code, and hold it in a temporary name, send it up. When we are finished generating this code for expression 1, we'll go up. The result of that code will be born in a temporary name, which will be sent up. And in a similar way, we'll do expression 2. Another temporary will be sent up from there. And then we'll finish off the processing at the op level by combining these two temporaries, generating code, stitching them together. And the result of that will be again a temporary, which will go up. So you can see that all this process is, all it's doing is generating code, holding them in a temporary name, sending it up, doing the same thing on the right-hand side, and then combining the two, generating yet another temporary, generating that, and sending it up and up and up. So here is the simple algorithm which I just mentioned, how that will operate. So we'll have a generate function at the op level, and that generate function will invoke the another generate function for expression 1. Its goal will be to generate the code for expression 1, and the result of that will be sent in a symbolic name, is being returned. So the return value here is a string name, which is being sent and which is being held in T1. And the second one is similarly invoked, the generate function on the expression 2. That is, its result is being, the code is being generated by the generate function. And the result of that code will be sent in a symbolic name through that generate function, and it will be held in T2. So now these two code generations have finished after the first call and after the second call. And now the main thing that is going on at the op level is as follows. We are going to solicit a new temporary name here, which is a new temp call, which is giving a yet another symbolic name, and then combining the result of those two names, which are coming in T1 and T2, through the op and generating this R. So the real code that is getting generated at this particular level is what is shown as an argument to emit, and that is the one which will get printed out on the output. And at this particular point, you can see the code generation at the op level is complete, and that is going to return as its result a symbolic name, which is in R, which is a temporary name. So let's say we generated some temporary called T10, which is in R here. Okay, that T10 will get returned back from this op to the caller of this generate, which will be yet another op node from which we have descended down. So you can see here we are descending first to the expression 1. Expression 1 itself might need further calls, because what is expression 1? The expression 1 might be represented another subtree here using op and its two branches and so on. And eventually you can see that these calls will go down to the lowest level, in which there is no more operator but just a name, which is, let's say, A plus B kind of a situation. So it will hit that leaf node at that particular point. As I mentioned earlier, either will allocate a temporary and copy A into that temporary and return T1 and its result. If you want to preserve, for example, the value of A in a temporary, or in other cases, it will directly return A as its result, just like at the return R, that will be either A, or it will return a T1, which is allocated. And then similarly, things will start happening on the other side. It will generate the sub-expressions. They will keep going up and up and up. And similarly, on the right-hand side, in this particular order, we will do the same thing, generate the sub-expression, generate the code, hold their result in typical names, which are getting sent up, and they are getting combined in terms of this op node. And that's how we'll finish any kind of sub-expression which is represented by this particular subtrees. So here is the higher level algorithm: generate the code for left and right children, get the registers or the names to hold their results, get a new temporary name here for finishing off stitching them together, generate the code for this operation at the current level, and then go up for the call above. And this is very intuitive and simple, and you can see here that this particular procedure will work well for binary arithmetic, unary, logical operations, any kind of expressions which need combining things together, which are consisting of multiple operations. So So at this point, I will pause and see if we have understood this core mechanism and see if there are any questions. And then I have a question for you guys just to make sure that we have understood it. So let me first take any questions in terms of if anybody has any questions about these.
There has been just one question. About 10 minutes ago, it was asked in chat, why do we need the transformation to be symmetric? We might have lost the context for that question. Does whoever asked it want to ask it again?
So remember, I think I kind of understand what the question might be. This is the most general mechanism. So, you may have sub-expressions on both sides. On expression 1, there might be a big tree sitting below it, and expression 2 might be another big tree which is sitting below it. And what we are trying to do here is have a generalized procedure which is able to visit both left and right hand sides in case of a binary operation. Sometimes there may not be any need. There may be only a unary operator attached to, let's say, an expression 1. In which case, of course, we will not do anything about expression 2. We'll get the temporary which is generated in expression 1. We'll then attach the operator to that expression. We'll have maybe a negation of value or whatever, depending on the operator. And then we'll send the new temporary up from there. So in this particular case, we are looking at the most general case, and we are trying to, of course, deal with the fact that we may need cogeneration on both sides of the house. A good example, if you want to sort of look at it, will be, let's say, A times B plus C times D. So A times B is the expression 1, and C times D is expression 2. And the plus operator is sitting at the top. And what is going on is we are starting with the top level subtree with the plus at the root, and then descending down to A times B on the left-hand side. Further down, it will descend from there to A and B and return T1 and T2 as temporaries. Let's say in this particular case, we wanted to keep a copy of A and copy of B. And those will be picked up at the star level and then converted into T1 times T2 and generate new temporary, which is T3 at that level, and send it up to the op. And similarly for expression 2, things will happen for T4 and T5. It will generate a T6 in terms of the star operation. And at the top level for plus, then I believe T3 and T6 will get added together and generate T7.
Yeah, my question was with regards to the slide where you were discussing translation from like lowering from higher level IR to lower level IR. There was a point there which said that the algorithm needed to be symmetric. I mean, I think it was even before this. Yeah, systematic. Oh, sorry, I just misread the slide.
All right, systematic. Yeah, not symmetric.
I just got confused. Yeah.
Okay. Sure. Okay, so if there are no other questions, then I have a question. What is the kind of operator? Can you say something here based on the call order that we are seeing for this generate procedure for cogeneration? What can you say about this operator which is being handled here? Can you say something about its property?
It has lower precedence than expression 1 and expression 2.
Okay, that's good. That is definitely true. And that would have reflected by the parse tree. And there is something else.
The IR defines that arguments are evaluated left to right.
Exactly. This is actually, you can see here that there is something about the associativity of the operator here, which is being implemented here in the core generation. You see that we are trying to evaluate this expression 1 in T1, which is fine. And then we are evaluating expression 2. So we are going on the left subtree first, evaluating that. And the way it is being combined is by processing these left subtree, generating this T1, and then T1 being combined with T2, and there is a left associativity being implemented here. Otherwise, what we would do is we would go to the right-hand side subtree, traverse that completely, and generate the IR over there first, and then come back to the left subtree, and then combine it in terms of the operators over there. So that is the order in which this occurs is really important. And you may want to think about an expression here, and that will be organized appropriately by the parse tree, which is in terms of taking the operator precedences into account and doing the organization in a particular way, and then you will descend that down, a to the power b to the power c, for example. You would try to do it by generating the code for the right-hand side IR, right-hand side operations first. Now you may say, oh, that's already reflected in the tree, so what's the big deal? That's not entirely true. The precedences are represented, but the order of evaluation is still the core generator's responsibility. And in cases where there are side effects and so on of the sub-expression evaluation, the order of evaluation is very important. So remember that simply relying and leaving it to the parse tree is only the job half done. Eventually, the core generator must evaluate it in that particular way. And that is why the order of call, whether the expression 1 is called first or expression 2 is called first, is extremely important. If there is a side effect, for example, in expression 2's evaluation, which has a bearing on expression 1 and the associativity is towards the right, you must evaluate that side effect and then only come back to expression 1. And that's why by putting this type of order, you will generate wrong code otherwise. I hope you get the point. And try to work out an example to convince yourself that the order here is left associative, which is saying that, hey, evaluate the left-hand side first, then go to the right-hand side, which is being reflected in the order of calls, expression 1 followed by expression 2. But if the order is right associative, then which says that evaluate expression 2 first and then evaluate expression 1, you must appropriately switch the order here. So that was the question, which is kind of missed, as sometimes in terms of the order of code generation is really the implementation order, and that must be preserved here. It's not simply left. It's not simply the job of parser, but the parser's job is, of course, to organize this in the correct way as per the precedences and associativity. But to even take further from there into generated code, we must follow the same operator precedences and which are there in the tree, going from the lowest precedence to the highest precedence, but the associativity is sometimes which is missed out, creating problems. So watch out for that. So let's move further. If you understood this, then the next complicated operators are and or. And as you know, they are short-circuiting operator, and they need some control flow implementation, which is what we'll use further in terms of if expressions and whiles and fors and so on. So this is a good point to implement and or operators. So the ones which we saw earlier, only we need to pay attention to the operator precedences and associated, as I mentioned, and descend down appropriately, generate code, and then come back, descend down on the other side, come back, and then stitch it together, things which are shown earlier. But in this particular case, the meaning of these particular operators is there in the semantics. So what is going on in terms of this OR operator is, first of all, it's left associative, and is being shown here as if expression 1 is true, if the result of this expression is true, do not evaluate expression 2. So do not execute the code for expression 2. That is what is the meaning of this. So how do we implement this? So first and foremost, you can see that it's left associative. So we'll have a call for expression 1, and we'll generate code for expression 1, again by calling its generate function. We'll assign, we'll take the result of that in a temporary symbolic name, T1. And then we'll hold this into a newly generated temporary at the current level, which is coming out of the new temp function. So new temp is an assist function which is generating the symbolic names, and new label is an assist function which is generating the labels where the transfer of control occurs. These are the two bookkeeping activities which we are definitely following here. So we generated a new name here, R, and we held the result of T1. Next, what we want to do is we want to insert a code which will check if T1 is true or not. So that is shown by the next emit statement. You can see here that if go to T1, we go to the label E. So what it means is if T1 is already true, if its result is already true, which is checked by this go to statement, then we are simply going to branch to E, which is the end of this particular construct, which is a placeholder for that. If the result is not true, we are going to have the code here, which is put there by the generate function for expression 2. So you can see it is very intuitive and simple layout, as though you will program in assembly. So you're following pretty much the same principle here. You are writing the code for expression 1 or generating it in this particular case through the generate function. You are then doing a check in terms of its result is true or not by checking the outcome in T1. If it's true, then you don't need to worry about the code for expression 2, which is sitting there, and you simply bypass it and you go to E, which is the exit label for this particular level of the OR operation, short circuit OR operation. And that's where you will simply send the result, which is in R, back up. However, if you need to evaluate expression 2, you will descend down and you have a generate call. Note now the placement of this call. It is actually after this if statement. So if the check fails, if it is not true, then it will fall through here. It will execute the code for expression 2. It will generate that in T2. And now at this particular point, you can see something smart which the compiler has done. We know at this particular point, after T2 is generated, that we are on a fall through path here. That means T1 must be false. So in some sense, we could have generated, to be really robust or maybe a little religious here, we would have generated code for T1 and T2 together, ORing them. But since the compiler knows that T1 is false here, it has taken the liberty of getting rid of T1 altogether from this thing and simply assigning R equal to T2, and because it's false, ORed with expression 2. So the result of R is really dictated now by T2, which is being assigned. If T2 were true, it will be true. If T2 were false, it will be false. But since it is OR already with something which is false, T1, we need not generate T1 or T2 as an expression, which would have been done in a normal way if this were not a short circuiting operator. So we will generate that, we'll hold it in R, and you can see at the exit point E, we know that the R is containing the right values. It is containing, in one case, just T1 if it were true. It is containing the result as T2 if T1 were to be false. And that's the result which is being conveyed back up. That part doesn't change. It goes back up using R. And again, depending on the outer operator, something similar will happen if it's a short circuit operator. If it's not, then it will continue in the regular way. It will evaluate both sides of the trees, and it will then group it together just like what was shown earlier in a non-short circuit manner. So is this part clear about the short circuit operator or implementation? It's very simple, but you can see that it does have a control flow generated here in terms of this particular statement, if statement that is getting generated. So what you will have here when you look at the generated code for expression 1 will be there, then followed by this temporary assignment through the emit. Then you will have if statement, and here is how it will look. This will be the generated code on the right hand side. You can see here that the part which has changed here is of course checking whether T1 is true or not, and then branching straight out or falling through, evaluating T2 and so on. So this is the way this short circuit OR operation will work. And you can see here that there was an optimization. I wanted to point that out. T1 or T2 has not been done. It's simply R has been assigned in appropriate ways. That's one optimization, which has already taken place, knowing the point at which we are generating this code. And the second one, which is kind of a little implicit here, is this, that as you know, the branches are not really good for execution, right? I hope everybody agrees. There have been tremendous progress in terms of course, the branch executions, branch speculation, and all kinds of branch prediction in the hardware, etc., etc. But regardless, the branches are bad because they disturb pipelines, and the next instruction in the pipeline is not there, and so on. So in short, the more linear dynamic path of execution, the more linear it is better for performance. I hope everybody agrees, because you have the next instruction in the pipe, and you are going to execute and pay almost no penalty for going that route. Although modern processors try to get around it through speculation by doing, prefetching and whatnot, and all kinds of technique that deploy branch prediction. Here, the assumption, so the linear dynamic path should be a common path of the code. And you can see here that that's the assumption. That it is quite rare case to see that the T1 itself is true, and we don't need T2. That is the assumption, because the dynamic linear path here will be a fall-through path of the if statement. So in other words, what is assumed here by the code generator is the common case here is that the T1 short circuiting T2 is a rare case. There is no way for a compiler to know whether this is true or not in general. But mostly the programmers use this as a corner case to cover a corner case. And that assumption is very true in what is assumed here. Why? So most of the time you use some short circuiting, as I said, is to cover some corner case to implement wherein you don't want the expression 2 to be evaluated under certain situations. So for example, if you're doing um, division in expression 2, and you want to check whether the divisor, the one which divides the numerator, is 0 or not, because otherwise you'll run into a division by 0 condition. And so you will check that if that is not equal to 0, then go ahead and do the second operation. Only when that particular condition becomes true is when you don't want the second condition to become 0. So when let's say a equal to 0 or b by a would be a good way to write this type of a statement. When a is equal to 0, just evaluate T1 and don't go for the expression 2. And that will be a corner case which will be covered for the soundness of the semantics, etc. by the programmer, and it will be a corner case, and most of the time you will be evaluating in short both of the T1 and T2. So that follows this particular programmer's intent or logic, short circuiting operators logic, and that's why this code organization is pretty much in which the fall through path here is a dynamic path, which is the most efficient path for evaluating this expression. Okay, so let's come to the overall organization of the code generator. The big function here is the emit, which is the printer, and it is the order of calls is really important at the right points. This is being called, and it is just generating the instruction, adding it to the buffer, and this buffer is containing the linear code. And the second function here is the new label, which will get us new destination for each one of the if then else kind of if statements for branching, just like what we showed earlier. So here was that statement, for example. We got a new label in E, and that was the place where we jumped in case T1 were true. So this is the second important call. And the third one is new temp, which is we have seen earlier. It's a new unique temporary name. And we'll generate this, we'll hold this temporary, its attributes in symbol table and so on. We may do certain maybe transformations later to get rid of certain temporaries through a variety of techniques, including most important being register allocation. Similarly, going forward, now we have and intent here is this, that in case the first expression now evaluates to false, there's no point evaluating the expression 2 because eventually the result is going to be false anyway. And that is being implemented by the code generator shown on the right hand side. So again, in a very manner which is very similar to the OR, what we are doing here is calling the generate function. That expression is always evaluated in T1, and the T1 is the return of value of that expression in a temporary name. The next one is emit function, which is holding that result in the current temporary that is generated at this level, which is R. So that is being assigned there. The next check is, of course, this is again very similar to this, the OR side. The next check is if go to T1 N. So if this happens to be true now, then we are going to jump to this particular label N, where we will find expression 2. And now we have the fall through of this, which means that this is false. If T1 were to be false, of course, we need to bypass the expression 2. And so we have a go to here, which is jump around the generated code at this particular point to a label E. And that label E is where the expression 2's code generation would have already ended. So it's at the end. We generate that and we jump across. And then coming back to N, where we are supposed to have expression 2's code, we call generate. That gets the generated value in T2. And now at this particular point, again, the similar type of optimization. So you can see here that at the point where T2 is coming out, we already know that the expression 1 is true. That's how we have come here. See that chain of branch here, that if T1 is true, then go to N, and N is where we are generating T2. So in short, it is a true and add with expression true that is being evaluated here. And that's why you can see that we have sort of gotten rid of this evaluation and made it simple. The net result of something ANDed with a true result is the expression itself as per the logic's rules. And that's why we have T2 here, and that will be the eventual evaluation of expression 1 and then T2 and then expression 2. And that's the one which will be passed further along. So you can see here that the this is one type of code generation decision which is could be taken by the compiler. Just to illustrate it in a different code layout here than the OR. You can see here that we are carrying out here a jump which is on the true side, and so we will go through this path of going to N, and then that's where we'll generate the expression results. We will combine it and we'll exit. That would be one dynamic code path. The second dynamic code path would be, of course, that the expression 1 evaluates to false. So we have a fall through here. And then we have a branch which is straight outside, an unconditional branch in E, which will exit things out of the things. So if you analyze these two different code paths in dynamic code paths, in one case we pay the price of going through a branch, a taken branch, going to N and then exit. In the second case, we fall through and go to this particular unconditional branch and then exit. The unconditional branches are a little less expensive because we know their targets, they're always going to go there and so on. And of course, the common code path that is assumed here is the fact that in this case, the first expression will be false in the common case. So the AND operator is used by many programmers in this particular way, in which the first expression happens to be false most commonly, and therefore we don't execute the second one. And that is the path, dynamic code path, which is reflected in this code generation decision layout over here. So again, if we have more profile information, etc., we could go one way or the other based on the way we see these branches behaving or the more common cases happening, etc. But this is the assumption I just wanted to point out, especially for this particular layout of the code generator. We can do something different as well. And here is the code generator for that, which is negated that particular expression. What we have here is something similar to what we had in the OR side. And we have again evaluated T1. Here in this particular case, we have checked if that really leads to a false branch, and then we execute that and go there. If not, we will execute T2 and then go down and so on. So in this case, you can see that one of the branches has been completely eliminated, which is the conditional branch, and it's a very simple layout structure, which again emphasizes the fact that the fall-through path may be the common path here. That assumption in this one, which is a different one than the previous one. So if the fall-through path is behaving in a similar way, that most of the time we are going to execute expression 1 and expression 2. So just like in the OR case, this will behave better because we will be going down that path, a linear path, through a fall-through mechanism, or if not, and doing both T1 and T2. Of course, if that's not true, then we will take a conditional branch, which is going to take us to E, and it will, of course, not be the common path, because the common path will be the fall through. So very rarely languages have mechanisms to even go further and show which are the branch biases or the predicate biases, etc. So the compiler many times makes this decision based on the usage of these things in the way the language is intended to be used, and kind of makes these decisions. If you have profile information, you can try to weigh in one layout versus the second layout for efficiency here. Okay, so that's basically it about the most of the expressions. You can see that this mechanism that we have takes an expression, breaks it down, generates the code, sends it up, combines it, and eventually equal to operator will also be handled in the same way. There will be a code generator which will have the equal to operator sitting at its top, and it will take the temporary on the right hand side and the left hand side and equate the right hand side to its left hand side counterpart in terms of implementing the semantics of what is the assignment statement. The left hand side, the only important question to bear there is the L value semantics is to be kept in mind in terms of the L value. So let's take a simple case like A is equal to B. The right hand side will probably return here the T1 for evaluating this B eventually. And on the left hand side, obviously you should not create a copy of A and then assign it to this, but rather keep the name as is and assign the T1 to this name to bear the L value semantics. And this becomes an issue. For scalar names, this is not a problem because the assignment operator and its left-hand side is immediately treated as L value, and the name itself bears the L value. However, this becomes an issue in terms of when the name is not a scalar, when it is an array and so on. So those are treated separately based on the indexing mechanism which is being implemented, and that's what we'll see now. Okay, so this is a simple array expression. Expression 1, indexing expression 2, and what is going on here is it could be some array name and some pointers and all kinds of things which are leading to expression 1, and some indexing expression which is again a little more complex in terms of expression 2. And eventually they will, so the calls are happening here as follows. And this is implementing the R value semantics of this indexing operation or array access operation. Again, what we are doing here is generating the result of this in A which is the base. You can see O is being the offset here, and generating the symbolic names which are capturing this base and offset results. We will take the offset and then if multiply it by size. That is going to give us the physical offset towards this. And then we have the second statement here, which is the base being added to the offset in terms of going to that particular element. And the last one you can see is really where the R value is being implemented. You're dereferencing this A, getting its value, and generating its result into R, that the temporary of this particular operation, and is being sent back up. This is the R value semantics, which is generating the base offset and generating the necessary load, which is to implement that difference. So this should be very clear. The size information is coming from the symbol table, and which is needed for doing this offset calculation at this particular point. Some other languages or some other IRs keep it the way it is also, and they don't generate this lower level stuff, but leave it at this particular array abstractions. What is the downside of it? That's a very uncommon practice. What is the downside? Why is it that we generate this base plus offset stuff? The answer is obvious. Obviously, in doing these array address calculations, for most machines, we are going to have a significant address calculation code, which is being exposed here by these operations. And that is one important target of optimizations. There are a lot of index A of I, B of I, they generate a lot of bookkeeping code for implementing the dereference on A of I or B of I. And that particular code, unless you expose it through IR mechanism, you will not be able to optimize it. So this is a much more common example. So far we can go ahead and generate now code for statements, which are arithmetic statements, logical operators, all kinds of different expressions could be embedded in them, but they had to be assignment statements. We could also have array index being referenced and used there. And in a similar way, we could also have the records and unions and etc., because their fields will then need some address calculation, which will be very similar in terms of processing their base, and then after the dot there will be their field reference. So we'll calculate both the expressions, and then we'll use those just like in previous case. Hiding the code will generate, for example, if this expression dot another expression, we'll just generate the code for first, the code for the offset, then we'll combine it and to dereference it using L value or R value, we would have generated the necessary code for records and things like that. So for any complex objects which are non-scalars, same strategy can be followed. And so when these strategies for scalars and complex objects, we can combine into assignment statements, we can pretty much cover all the statements in a program, because remember, each statement is completely independent of the other. In this particular case, it is not nested statement. So it's a series of, let's say, assignment statements. So we complete code generation for first assignment statement, then we go for the code generation statement for the second assignment statement, and blah, blah, blah. You may ask me, so then how do we make sure that these codes interoperate well with each other? that is decided by the program. That is not decided by the compiler. You can easily see there the programmer's job is to make sure that the output of one statement goes into the input of the next or the next to next statement and so on. So in short, the data flow of these values is governed by the program and is governed by the names which are used in the L value and R value sense. And they're left intact by the compiler. They are also following the lexical order, and that's why they generate the correct code eventually. What is being generated by the compiler or tackled by the compiler is how do we implement each one of these statements internally by decomposing expressions, sub-expressions, making sure their data flow or the short circuit operators or any other thing, their data and control flow is correctly implemented. That's being governed in the right order of precedences, right associativity. That's being in the compiler's job. Now what is left is, of course, conditionals, loops, and all these kinds of statements. So, which is not very difficult to see given our understanding of short circuit now. So let's say if we have if expression and statement, how can we deal with it? So this is a statement by itself, and of course, here our job is to implement the construct or the statement, whatever you want to call it, correctly. So first of all, how do we know that this is an if statement? So obviously we know it from the label of the AST node that this is not really an assignment statement, it's an if statement. And it will have different fields. It will have a syntactically a conditional which will get evaluated, and then a statement or groups of statements in its body. So first we encounter, once we decide that this is a if statement kind of a AST node, what we'll do is we'll take this first field, which is an expression, and generate code for it. In the same way, this will be some kind of a conditional statement, its outcome will be Boolean and blah, blah, blah. It might consist of some sub-expressions which are arithmetic, and they will get called upon by the corresponding AST nodes. They will generate their code. Eventually, the top level node there will be a conditional, and making sure it is a conditional will be the job of semantic analysis, that the outcome here is Boolean or binary in terms of value and not something else. So those checks would have been passed already. And at this particular point, we'll generate the code for the topmost level statement in terms of its Boolean outcome. And we'll hold it in T, which is just like we are processing any other thing earlier from the sub-expressions of this expression. So once we do that, next we will be simply checking if the outcome of this is true or not. And this is a simple emit statement, which we are inserting here the if statement. If not, we have then go to on T on E. So what it means is if this expression's result doesn't happen to be true, then we are simply going to bypass the group of statements because we don't want to execute the if statement. It's going to simply execute, and that's why we have put this check. So when this is false, we'll simply bypass it. Otherwise, we would generate the statements code. Again, the generate statement for these statements will be either, in this particular example, might be assignment statement. It could be another if statement, and it will invoke appropriate code generator because each code generator has its own, each kind has its own code generator, and then it will put that code over there. One thing you can easily see here that is really important is that the use of labels here as well as in past examples, whenever we use labels, we implemented a control flow. And what we carefully did was this, that we generated a new label, and that label told us where to jump for. So that's how we symbolically structured it. So the jump location, we don't know where it is, but we don't need to know. So for example, when we generate the emits statement there, the third statement in this right-hand side, if not go to TE, we don't know where the jump will be because we don't know how many statements are going to be there in the body. We don't know how complex are they, whether they are going to be nested if then else, nested whiles, all kinds of different things. All we know is this, that once they are finished though, that is the place at which we are going to jump. And so that is associatively mapped here by not noting how many places to jump, but rather making an association with a label. So as long as we have this label L5, L7, whatever that is generated here by a new label, we know that symbolically it corresponds to the place to jump. And that's how the code generator will track or maintain the association between the point from where you're jumping and to the point where you're jumping by simply creating the label that brings this correspondence into picture. And doesn't really have to, unlike assembly programming, etc., which are based on number of locations you bypass. We don't have to do any of this, and we shouldn't do any of this. So the labels therefore play a very important role in terms of finding out where to jump, and their placement is quite simple that way in terms of they typically demarcate a construct. Very rarely, and there are examples though, you do have to pass the labels around, typically from inner scopes to the outer scopes, because you are able to jump like that from one scope to the outer scope, and you may sometimes just terminate a whole bunch of executions based on where you're jumping. And for that particular matter, the labels are needed from to carry out the jumps for termination of the inner execution into the outer execution. But almost inevitably, we don't need it to jump inside because jumping inside is not typically allowed. Jumping in the middle of a loop is not allowed by almost no programming language allows. So going deeper, you don't need the labels from outer scopes to the inner ones, but reverse you do need. And you have typically processed the outer scope in terms of its label generation. And once you go and descend down in the inner ones, those labels are available for you to take the branches on. So that's typical, and that's why this mechanism works well there as well. Loops, very simple, very similar to the other control constructs. While expression statement, very typical example. And again, let's look at it quickly in terms of what's going on here. We'll try to wrap this up, and then we'll just stop in a couple of minutes. And we're almost through here. So the expressions, you can see again what we do here is we want to be able to loop back again and again. So we have a new label at the top. We do have evaluation of this expression, hold it in T. When the expression is false, we have a branch out in if not go to. And then if it is not branched out, we have a generate statement, of course, to implement the body of while. And then we do have a go to T, an unconditional one, which is interesting because we are continuously executing the while statement at the top level at T. and then we just have an exit E. So it should be fairly easy to see the here, which is put a label. So whenever you generate do a code generator for a construct, let's say if I ask you that this is the way this construct behaves and blah, 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 what you should do is first do a layout the way it is shown here, that, hey, I need a label here. I need to do this check here. I need this bypass here. I need this conditional go to back here, and then fill in the template, and it's all about that. And that decides your code generator. And you can see here that it's fairly simple of top level loop back branch point, then expressions evaluation. Then that's the next one is if it's false, branch out, otherwise stay inside the body into a go to, and so on. The last one here is function calls. Most of the time, what really has to be done as far as processing these function calls is we had to evaluate the parameters at the point of call, push them onto the stack, and then wait for the return value. That's all at the call site. And then, of course, the code generator for function itself will have its own assignment statements and so on. So that won't change at all. But at the point of call, we typically would be evaluating these expressions. So here it is, the code generator for the call site. Each expression will be evaluated through a generate call. The order of evaluation typically is from left to right. Again, important one because of side effects and all this. And then we have a push TI, which is each of the temporaries for parameter passing. Then we have a jump for the function name, which is generated earlier through the first generate call. Remember that F could be an expression. So that is why there is a generate call there. Could be a pointer arithmetic, etc. there. If it's a function pointer, or array of functions, etc., whatever through pointers. So that's why there is a generate call which holds it in A, and then there's a call to A, and then finally we are waiting for here the get result and get back to X. So that's what is typical mechanism. This assumes that we have what is called as an eager evaluation mechanism for function. That is, all the calls arguments are evaluated before the call. The for loop is very similar. I'm kind of going to leave that to you. Again, there will be evaluations of expressions, labels, placeholders for unconditional returns, exit conditions, increment conditions, things like that. It's pretty easy to see how the for semantics will get implemented. So do this exercise, generate a template, and see how this will work. Last but not the least, the difference between R value and L value, especially for arrays and other complex variables. Just a quick note on that. We already saw how the R value is handled for arrays. Let's see how the L value will be handled. So first of all, whether it is R value, L value, that will be deduced using the AST. And the context of the code generator will be noting it, in this case, that AI is to be implemented as L value. And so we'll have an L generate, which is a simple function, which will look pretty much similar. This was the R value function, in which case we had the base plus offset, and we did a load. The value of the load was returned back as the evaluation of this R value. But in this particular case, things will be simple. The L value means it's a location which is being returned here, and that location is A, for example, which is being the point of this arithmetic, base plus offset, and then eventual assignment function will generate a store of the a particular value into A. So in this particular case, it's shown how we'll generate the L value, first of all, through L generate. And then the assignment operator itself, in this particular case, will be evaluated by generating this emit statement through a store that the R is being assigned through a pointer dereference of star L, and net result of this assignment is returned as R. You may ask me why. This is because of typical cascades of assignment operators in C and things like that, which is generating the correspondence of R value is being returned as the net evaluation of this. So note that particular point also. So there is not much further to look at. We'll stop here. Just that this is the generate function which operates at the AST node root level. And again, based on the type of AST node, it will call different types of functions, and it will get the right the values, and it will keep going back and from bottom up and generate the necessary code. So the only two things which are being shown here is the case of leaf nodes, wherein you have either a constant, we get that value and send it back, or a case of a name, which is being treated as an R value and sent it back. So that's about it. Sorry to go a little bit of time, but we'll stop here, and if anybody has any questions, we can talk in the office hours. Thank you.